All right, we'll get started. Hello and welcome to this session. Hi, I'm Chinmay Soman, part of StarTree, and we have Neha Pawar, also part of StarTree. All right, so today we'll be talking about three prominent real-time OLAP databases: Apache Pinot, Apache Druid, and then ClickHouse. In this talk, we'll briefly touch upon why real-time analytics, in case you still need a refresher. Look at the high-level architecture of the three systems, and then do an in-depth comparison of these three systems layer by layer in the talk. And then we'll summarize all our findings towards the end. Pretty much everything we'll talk today has already been documented in a long-form blog. You can check it out. Be sure to check that one. You can reach that at s3.ai/compare. And then since this is a very dense talk, we'll keep questions at the end. We'll leave some time for questions. All right, so let's get into it. As you have heard so far, real-time OLAP, or online analytical processing, is everywhere. Right? So gone are the days when you generate these dashboards and reports using traditional batch analytics, where the query latency could be seconds to minutes, data could be hours delayed, and mostly internal users consume these things. Modern applications nowadays have embedded real-time insights. For example, LinkedIn's feed relevance or Uber's personalization. In this case, the query latency has to be in milliseconds. Data has to be as fresh as possible. And then this is being consumed by millions of users across the globe. So to solve all these use cases, we have three prominent open source real-time OLAP databases: Pinot, Druid, and ClickHouse. We'll be focusing on these specific versions of these databases because things are changing all the time. By the time we are done speaking, something is probably obsolete. Lastly, we'll also look at the commercial offerings of these databases wherever appropriate. All right, so this is sort of a 10,000 feet view of all the three systems, how they look like, right? Pinot and Druid are actually quite similar. They have the data layer consists of servers that host segments in a columnar format for both real-time and historical data. They both have a deep store for data archival and also for other important reasons. They both have a query layer, which does a scatter gather across the servers. And they both have coordinator, controller, and zookeeper for doing some of the cluster coordination activities. ClickHouse, on the other hand, it has far fewer components. As you can see, it has a data node where you can host data, but it can also serve queries. And there is it needs zookeeper or ClickHouse keeper for some of the replication and coordination activities as well. So architecturally, ClickHouse is way simpler, very easy to get started. But on the flip side, even though Pinot and Druid have a lot of moving parts, that actually makes it easier to scale up in large cases. And fundamentally, I think they're just easier to operate because of the ease of moving things around, as very flexible to set up. All right. So to actually compare these systems, we came up with a layered architecture that you see here to form a common language for comparing across all three databases. So on the left here, we have the data sources, right, and then the use cases on the right. And in the middle are all the important layers that constitute the OLAP DB, right? Things like ingestion, storage, indexing, query, and so on. So throughout the rest of the talk, we'll go through layer by layer and go through the details of each system in that case, starting with data sources. So this is, again, a high-level view of all the important data sources and how the three systems compare in this regard. As you can see, Pinot actually does quite well for ingesting data from real-time sources like Kafka, Kinesis, PubSub, and so on. Both Pinot and Druid do fairly well for batch sources, like getting data from S3, GCS. And pretty much all the systems need to still keep improving and fetching data from SQL sources, as you see. One thing, as you will note, ClickHouse actually has quite some limitations across the board, and we'll be discussing why in the next few slides. All right, so let's get into ingestion. Ingestion, as you might all imagine, is one of the most complex problems in databases. How do you get your data into the DAM system is one of the hardest problems. And there are many aspects to ingestion, so we'll go through it one by one. Starting with real time. So real time is basically when you want to get data from like Kafka into the system and then query that data. And there's usually two models of doing that. One is a pull model, where you fetch data directly from something like Kafka. And there's a push model where applications can write directly to the OLAP database. The pull model is generally more commonly used, more prominent. And both Druid and Pinot do a great job of pulling from these sources. ClickHouse, on the other hand, actually does not have a real pull model. So it does have things like a Kafka engine, which can pull data from Kafka, but you can't query that table. So you need a materialized view and a separate table to actually query data from real time. So it's actually a quite complex multi-hop setup for ClickHouse. And there's other limitations as well, as we'll see in a minute. Push model is oftentimes also needed. In many cases, believe it or not, your data might not actually be in Kafka. And in that case, you need the ability to write data directly to the DB, or you may not have connectivity to your real-time sources. Again, this is important. ClickHouse here actually does have, of the three systems, it does a great job at actually supporting push model. Moving on, both Pinot and Druid do a great job at ingesting large amounts of data, so very high throughput ingestion, and supporting exactly one semantics. And all the systems do a good job of handling out-of-order events or late arriving events. Let's take a quick deep dive into the Kafka support. Kafka is one of the most important real-time sources. So it's important to understand how each system does Kafka ingestion. Pinot and Druid are very similar, so in this case, we'll only compare Pinot and ClickHouse. So in addition to the complex setup I described with ClickHouse, it also uses the high-level consumer, Kafka consumer, or the consumer group approach for ingesting data, which is susceptible to a bunch of challenges. As you can see here, chances of duplication, difficulty to scale out, and in general, fault tolerance is also a challenge. Whereas Pinot evolved to using the low-level consumer, which solves a lot of these issues. In addition, ClickHouse recommends going with very large message batch sizes when fetching from Kafka. So think of like 500,000 to 1 million messages every time you fetch from Kafka. So this is good for handling high throughput, but it has direct impact on the freshness of your data. So your ingestion latency increases the larger the message size. So you can't query the data as quickly as possible. Furthermore, it is also limited by the number of Kafka partitions. It's difficult to scale a ClickHouse cluster beyond the number of Kafka partitions when using the Kafka table engine. And then there are other things, for example, chances of data duplication, which could actually happen even if your Kafka stream is perfect. Even if there's no duplicates in your stream, you could still end up with duplicates during the ClickHouse ingestion. And they also use Zookeeper in the fast path for replication, which is quite a bit of an overhead architecturally. And then finally, they don't actually use Kafka engine in ClickHouse Cloud. They actually recommend using something else for their commercial application. All right, let's also take another deep dive into upserts. Upserts is one of the most important things in real-time ingestion. So, as much as you would want to believe it, but your real-time streams are not perfect. They'll have updates, they'll have deletes, they'll have duplicates, and we need to be able to handle that well. Companies like Uber, Citibank, they rely on this crucial feature to support many of their critical business use cases. And surprisingly, Pinot is the only one that actually has real-time upsert support in terms of full row upserts or partial row upserts or ability to handle duplication or even scalability in terms of handling billions of primary keys. Druid does not have any upsert support, and the support in ClickHouse is pretty limited. So you could do some things like lightweight deletes are supported, but most of the for frequent updates, they recommend using an asynchronous model, which is not really real time. The way Pinot is able to do this is using this kind of an architecture. So the design principle is to reconcile upserts during ingestion. So there's very little query overhead. So as data comes in, each Pinot server is updating the upsert metadata and a per segment bitmap. This bitmap allows us to quickly filter out obsolete records during query. So you can very little overhead during both ingestion and query. And what's more, with StarTree, we also made it easier to handle billions of keys. So by reducing the memory pressure that was originally there in the original upsert design. Of course, we are not done here with upserts. The new things that we are adding soon, things like TTL, time to live, for the primary keys, compaction, and a native backfill support for upserts. All right, moving on to batch and SQL ingestion. So batch ingestion is where we want to fetch data from things like S3, GCS, and even SQL systems. And both Pinot and Druid have a pretty good support for native support for fetching data from these external systems. So you don't need to rely on a different ETL pipeline to fetch your data, which is very convenient. This support is limited in ClickHouse. They do have some S3 support, but not really a scalable approach. Pinot also has a great support for using Flink and Spark to sort of push large segments into Pinot as a push model. All three systems do well in terms of handling the different data formats like Parquet, ORC, CSV, and so on. And Pinot and Druid in particular actually have, again, good support for backfilling. Given a time range of data, we can go and efficiently backfill, giving you exactly one semantics. A special case of batch ingestion is SQL ingestion. So you want to fetch large amounts of data from your SQL sources like Snowflake, BigQuery, MySQL, and so on. Again, Pinot and Druid have native support for doing this across both in a one-time large bootstrap or even incremental fashion. They both support that. ClickHouse so far does not have any such support. All right, so quick deep dive into how Pinot is actually doing this native fetch. We use a component called a Pinot minion, which can run these background tasks. These tasks go and fetch large batches of data, convert them into Pinot segments, and then push them into the live cluster. This is great because there's very little overhead on the actual query serving nodes on the cluster. And then you can easily scale out the tasks as depending on how big your ingestion is. And of course, it's very easy to use. And finally, pre-processing. This aspect is very important to reduce the friction during ingestion. Pinot and Druid have very good support for value and type transformation. So think of like flattening, data type transformation, filtering, and so on. They both do real-time roll-ups well. So think of like aggregating data as it's coming in and using different kind of aggregation functions. All systems do well in terms of batch rollups, but Druid in particular actually has very good support for SQL-based pre-processing. They recently launched their multi-stage engine, which makes it very flexible to transform data in a SQL declarative manner during ingestion. In addition, both Druid and ClickHouse also have limited denormalization support, which is useful for query optimization. And unfortunately, Pinot does not have these two features at the time. All right, so for the next set of slides, Neha is going to take over. Thank you.
Awesome, thanks, Chinmay. So now that the data is ingested into the system, we're going to look at the next set of layers, starting with storage. So we're going to look at storage at a few different levels, at the column level, segment, server, and then at the cluster level. So all three systems have a columnar storage format, and they're more or less similar in terms of the encoding and compression schemes that they support. So coming to segment and server level, let's talk about data layout. So what are the options available in each system for you to control the layout of the data in the segment and on the servers? all three systems allow you to choose a custom set of partitioning keys, whereas only Pinot and ClickHouse let you choose a column of your choice to be the primary sort column. And then when it comes to data assignment on the serving layer, Pinot is the only system that has controls for you to set smart assignment strategies for segment to server mapping. Now, why are we talking about this? Why is this even important? Given that Pinot has support for all three of these, let's take an example of a Pinot cluster to demonstrate how these techniques help at various points in the journey of a query. So let's say you get a query, it comes to the Pinot broker. On the broker has to figure out what are the servers that it needs to fan out to. On each server, the server has to figure out the segments that it needs to process. And then within each segment, we have to find the documents that you need to process. Then an aggregation happens on the server, and then a final aggregation happens on the broker. Now at each of these points, these optimizations and data layout techniques help Pinot reduce the amount of work that is done, and that directly impacts the query latency and helps in improving throughput. So firstly, at the broker level pruning is done, which helps you reduce the number of servers that you fan out to. And this is important because this helps you cap your long tail latency. Your query is going to be as fast as the slowest server. So especially when you have high throughput workloads, it's good to be able to cap the number of servers that you are fanning out to. And this is only possible if you have smart server to segment assignment strategies. For example, you could create server pools that are partition aware, or server pools that are replica groups, or server pools that are aware of availability zones, and then use that so that when you get your query, you are only going to a subset of servers and not trying to just scatter to all the servers that are available. Next, you have pruning at the server level, which helps you reduce the number of segments that you fan out to. And this is done using techniques such as metadata that is stored in the segment, and that can be again partitioning info, min-max column values, or Bloom filters. And then finally, once you get to a segment, you have to scan a column. And here, if you were able to sort that column in advance, then you're going to have better data locality and enable some smarter encoding techniques so that you minimize the amount of work you're doing to find the matching documents. Next, we're going to talk about data layout at a cluster level. And the interesting thing here to talk about is tiered storage. That is the ability to split your data as hot and cold onto various storage tiers. So each system claims to have tiered storage, but the way it is implemented and the kind of storage tiers that you can support has a huge impact on the cost to serve that you actually reduce and the latencies that you can achieve. So the way this is done in Druid, every time you need a new storage tier, you would add a new compute node pool, and that node pool is going to have your new storage tier. There's some limitations here. You can only use local storage options as your storage tier. And also in this model, so as your data volume starts growing, you have to keep adding more and more compute nodes to support those disks or disks and SSDs. And that's not really a very good model, because increase in data volume doesn't necessarily translate to an increase in your query workloads. So that means you're going to add a lot of compute nodes which might just be underutilized, and that won't be very good for your cost to serve. So the way to achieve best of both worlds in terms of cost and latency in tiered storage is if you are able to use a cloud object store as one of the storage tiers, and use that along with also having tightly coupled storage options in your cluster architecture. ClickHouse is able to support this kind of tiered storage, and so is Pinot in the StarTree cloud offering. So Pinot's version is very flexible. You can still use your cluster in like a fully tightly coupled mode, or you can use it in fully decoupled mode, or you can go for a hybrid approach where you have some nodes dedicated to local storage, some nodes dedicated to remote storage. And then you can split your data very flexibly across these tiers and query it all seamlessly as though you are querying any other table. And plus several investments have been made in Pinot's tiered storage to help combat the latencies that you might typically expect, the latency issues that you might expect once you start using data directly from cloud object storage. So for example, in Pinot, Pinot strictly stays away from approaches like lazy loading or anything that is going to have to download the entire segment file, and anything that relies on having local storage or having like a local cache. In Pinot, we're always trying to do a columnar fetch, selective columnar fetch, sometimes even go beyond that and just fetch relevant blocks within the column. Data is fetched smartly during the planning phase, and there is some smart pipelining of the fetch and compute, and that really helps us kind of get a head start in fetching the data and being faster while fetching from cloud object storage. Even though the data is on a remote tier, you can still do operations like altering the data, reindexing the data, changing the layout. And you can use every possible index that is available in Pinot, even if the segments are on remote. In ClickHouse, if you wanted to use the indexes that are available, you have to enable a local cache and then cache those indexes locally. In Pinot, we never rely on any caching approaches, but you can turn this on if you want additional optimizations, and those caches work at a column as well as an index level. Cool, so next layer that we're going to talk about is indexing. So bringing this diagram back, we talked about pruning at the broker level, server level pruning, and then at the final level, we just talked about if you had a sorted column, then that can help you minimize your data scan and reduce the amount of work done. But what really helps at this level is filter optimizations and aggregation optimizations in the form of indexes. So indexes help you create smart data structures, smart specialized data structures where that help you minimize the amount of data that you're scanning, and that helps you keep the query performance optimal and predictable even as your data keeps growing or as your throughput keeps increasing. Indexing is one area where Pinot really shines. So we have the classic techniques like inverted index, which all three systems have. We have the sorted index, which is available in Pinot and ClickHouse. And then the next set of indexes are very unique to Pinot. We have the range index, which is very useful for range queries like timestamp greater than, timestamp in between. Then we have the JSON index. So if you have semi-structured data, complex nested JSON objects, you don't need to invest in pre-processing jobs to get your data into structured form. You can just ingest it as is. The JSON index will kind of index every field in your complex payload, and you'll be able to query it really fast. If you have location data like geo coordinates, you can use geospatial indexes to query that really fast. Then we have the timestamp index. If you have like a very fine granularity timestamp column, this index lets you dynamically create rollups and also index those rollups so that you can save doing any sort of rollup computation on your timestamp columns during the query. Then we have the text index, which can be used for free text search, regexp-like queries, very useful for log analytics. And then we have two techniques for enhancing the pruning. We have the Bloom filter, which is for segment level pruning. This is available in all three systems. And then we have the sparse index, which is again for pruning, but for pruning out blocks or chunks within a column. This is available in ClickHouse in a limited capacity. You can only set it for the primary sort column. In Pinot, this is available in the StarTree cloud offering. So here's like a high-level overview of the power of indexing. We have some graphs here which compare what the latency was with and without that corresponding index. And you can see that with indexing, the latency reduces by several orders of magnitude, even when you have specialized data like JSON data or geospatial data. So far the indexes we talked about were columnar. StarTree index is one special index which is a segment level index. It serves as a filter as well as aggregation optimization. So StarTree index lets you maintain pre-aggregated values of certain dimension combinations, and you get to choose which are those dimensions and also how many values you want to store at each level. So let's take an example. If you had data with columns like name, environment ID, type, value, and you decided that you only want to create pre-aggregations for name and environment ID, and anytime you see that a particular combination has 10 or less records, you want to stop materializing further. So this is how your StarTree would look. You would start with the root node. At the first level, you would have the name column. Under each name, you would have environment ID. And finally, you would have the pre-aggregations stored at the leaf node. And anytime you see that, oh, this particular combination has less than 10 records, we would stop doing further materialization there. So in a way, StarTree lets you strike a balance or choose your overhead between pre-aggregating everything, which is like creating a traditional materialized view, and doing everything on the fly. So now if you get a query like this, where you have a filter on name and environment ID, this is going to be just a quick tree traversal and then one lookup for the aggregated value. So StarTree index is Pinot's way of building a intelligent materialized view. In a traditional materialized view, you would have to materialize all combinations of the selected dimensions, and that can lead to a non-trivial storage overhead. And given that StarTree index is built in Pinot very natively, like an index, it's very easy to create it, very easy to backfill it for older segments, or to keep it in sync with changes to the data. Versus in traditional materialized view, for example in Druid, to create a materialized view, you would need external data pre-processing workflows, and same if you had to do any backfills or keeping it in sync. In ClickHouse, though you don't need external data workflows for creating the index, it is quite a manual process and quite an overhead if you wanted to do backfills or keep the view in sync with changes to the data. And again, since StarTree index is a native index packed in every segment in Pinot, the query engine just picks the right index during query. Versus in the materialized view approach, the queries need to be aware of the materialized view, and also they need to be able to target the specific view during query. So with that, we come to the next layer, which is the query layer. Here we're going to talk about some basic and complex query constructs and query caching. So all three systems have a good support for basic query constructs like the filter, aggregation, group by, order by. They also have good support for sketches, which are needed for fast approximations. So coming to complex query constructs, starting with pluggable UDFs. So each system has some mechanism for you to be able to write like a custom UDF. For example, you can use Groovy functions in Pinot, or JavaScript functions in Druid, Lambda functions you could define in ClickHouse. But sometimes your logic might be too custom or too complex, and you might not be able to define it in these mechanisms. So in Pinot, you can write your UDF logic like a native function, package it in a jar, and then plug it into the system at runtime. Next, we come to the multi-stage query engine. So this is useful if you wanted to do complex queries such as joins, window functions, and if you try to do this on a single stage scatter gather, you're going to hit like resource, memory, network bottlenecks. So both Pinot and ClickHouse have a multi-stage query engine. Druid does have a multi-stage engine, but it is more used for ingestion because it's creating tasks, batch tasks that are submitted to the indexing service. ClickHouse is the only system that has support for window functions as of now. In both Pinot and Druid, this is a work in progress. And as of today, neither of the three systems have a very good joins story. So in Druid, you can only do lookup joins. That is where your write table data has to be preloaded, that is replicated on all nodes that have the left table data. So naturally, this only works for small dimension tables. Pinot also supports this kind of lookup joins. ClickHouse executes joins as broadcast join. So all the data from the write table after filtration has to be shipped to all the nodes that contain the left table data. And this works really well if the data that is being shipped or the number of nodes that you're shipping this data to is small enough. Pinot is the only system that's doing joins like a shuffle hash distributed join. So this is where your left and right table data after filtration is hashed and then sent to an independent shuffle stage. And this join is not impacted by the number of nodes that you have to ship your data to, but it might not be the best strategy in cases where the right table data was small. That is where broadcast would just have been a better choice. And then we come to query caching. So Druid has the best support for this of all three systems. There's a broker cache for per query results, a server cache for per segment results, very good eviction strategies to get rid of stale entries as soon as the data changes. ClickHouse does have a server-side cache for query caching, but the eviction is only done based on TTL, so there is a possibility that you can get incorrect results. And to wrap up this section, we're going to talk about query performance. So benchmarks are usually very dependent on the data set, on the query patterns, and on the use case. So it's always recommended to do your own benchmarks. But we'd like to share some numbers that were done in benchmarks by some neutral third parties. So these are some numbers shared by the WebEx team at Cisco, where they found that in their comparison of Pinot and ClickHouse, Pinot was 4 times faster than ClickHouse in most categories and able to maintain the P99th even as the query load increased. Then Zomato shared in a meetup that with the same cluster size, Pinot was able to achieve twice the amount of queries per second as compared to Druid. In this blog post shared by Confluera, they saw that Pinot queries were 2 to 4 times faster as compared to Druid and were able to sustain an increased query workload. And finally, in this benchmark conducted by YouGov, where they compared a bunch of systems, they found that Pinot was 5 to 7 times faster as compared to Druid and ClickHouse. And now that we've talked about several layers from ingestion all the way to query, let's talk about cluster management. Here we'll talk about availability of flexible options for cluster setup and ease of cluster operations. So let's start with talking about multi-tenancy. Multi-tenancy is the ability to host tables of multiple use cases in the same cluster by creating physical logical isolations such that the query and operations of one use case don't affect the other. So Pinot is the only system with a true multi-tenancy concept. Tenant is a first-class concept in Pinot, and that lets you create isolations amongst the brokers and servers of a given use case. Next, talking about high availability, or this is where you, the ability to keep your service available through partial component failures. So both Pinot and Druid have good support for this. Your components can be scaled independent of each other, data can be replicated easily, and the queries, ingestion, cluster operations, background tasks, they all keep running in the event of partial component failures. In ClickHouse, in general, due to lesser number of components, such as no deep store or sometimes optional ZK if you're just getting started, and also due to lack of separation of concerns, like many operations are just bundled into that single ClickHouse server, or many functionality is just skipped. Because of that, high availability is much harder to achieve. And for those same reasons, it's much harder to do operations like scale up, scale out, redistribute your data, or do node maintenance in ClickHouse. It involves a lot of manual operations like copying your data over to the newly added nodes and so on. And again, the mechanisms for permanent backup and then doing a recovery of your cluster using those backups is a little manual and cumbersome in ClickHouse. Next, we're going to talk about security. So all systems here are more or less the same. Druid and ClickHouse have Kerberos-based authentication. Pinot and Druid have OIDC-based authentication. Druid and ClickHouse right now have RBAC. Pinot has ABAC support in the StarTree cloud offering. And then ClickHouse has inbuilt support for encrypting the data, versus Druid and Pinot rely on the storage layer to provide the data encryption. Next, coming to cloud deployment model. So here we'll talk about ease of deploying these systems as a fully managed cloud solution via the commercial database as a service providers. So there's two ways to do this: full SaaS, where the cluster is provisioned in the vendor's cloud account, and the customer has to ship all the data to this cluster. And then bring your own cloud, where the cluster is provisioned in the customer's cloud account, and the customer retains full control of their data. So all three providers have very good support for the SaaS model. When it comes to bring your own cloud, ClickHouse Cloud does not support this model. Imply does support this model, but there are limitations, like you need VPC peering. StarTree Cloud has the best support for this model. So firstly, you don't need to do VPC peering with the remote data plane. That makes it frictionless to deploy and also scalable across multiple deployments. StarTree Cloud operates with the principle of least privilege. So the data never leaves the perimeter of the customer's cloud account. And at the same time, it is fully managed. You get the same SLAs as the SaaS model. And it's highly customizable in terms of the instance types and storage types, so you can make it very cost effective for your use case. And then finally, we have outbound connectors. So Pinot needs some improvement in this area. Both ClickHouse and Druid have a very rich support for several outbound connectors. And with that, we have looked at all the layers. So here's a quick summary of the comparison that we did. Starting with Pinot. Pinot has the best in-class indexing, very smart data layout techniques that help it perform really well at scale. In ingestion, it has very good support for real-time and batch ingestion. It's the only system that has real-time upserts. The cluster management is easy, only system with true multi-tenancy support. It has the best in-class cloud tiered storage and a very flexible cloud deployment model. The areas where it needs improvements are the outbound connector ecosystem is kind of small. The support for data types is low compared to ClickHouse, which has a very wide variety of data types. There is no SQL-based approach to do data pre-processing, and it needs some security improvements. Now coming to Druid, it's also designed to handle large-scale data. In ingestion, it has very good support for real-time and batch ingestion, great support for data pre-processing during ingestion, and has a very flexible SQL-based ingestion method. The cluster management is also easy in Druid. The areas for improvement, there's no real-time upserts, no push-based real-time ingestion. The indexing support is limited, and their tiered storage does not have a cloud object store option. And finally, ClickHouse. ClickHouse is the easiest getting started experience, least number of components. They have the best real-time push model, wide variety of data types, and very rich support for outbound connectors. But the support for pull-based ingestion is kind of weak. Then the limited indexing hinders the query performance on a large scale. And also because of the lesser number of components and lack of separation of concerns, there are operational limitations, especially when you try to run this at a production level scale. And with that, we are at the end of our tale of three databases. Thank you.